Hey, what's up, guys? It's Jack Callahan, and I'm going to teach y'all about the Compton Effect. Hope y'all enjoy. So, the Compton Effect was introduced by Arthur H. Compton, Nobel Prize winner, in 1923. He came up with an experiment to test the Compton Effect in order to further justify how light travels in packets called photons. So now that we know when and who the Compton Effect was started by, what is the Compton Effect? Well, a basic definition of the Compton effect is the decrease in energy of a photon as a result of electric scattering either by a proton or an electron, but usually by an electron. This decrease in energy results in an increased wavelength between scattered X-rays and incident X-rays. Okay, so the phenomenon probably seems a little bit confusing after the definition I just gave, so I'm going to show you a visual example of the Compton effect. So as a visual explanation of this effect, Compton assumed that photons act as particles, and the collision between two particles can be described with two basketballs. So throwing these basketballs together like this is a good visual representation of when particles collide. Both of particles, or basketballs, each have energy and momentum, and both are conserved in this inelastic collision. In another case, the incident photon can collide with an electron with an initial velocity of 0. In that case, the incident photon transfers some of its energy and momentum to the electron initially at rest, like here. After almost breaking my window with that last throw with the basketball, I hope I gave each of you a good visual representation of the collision between photons and the Compton effect. So now you guys are probably wondering, why does the Compton effect take place? Well, the Compton effect occurs because X-rays from the incident beam are scattered at multiple different angles by electrons, including carbon. So why does this matter? Well, the Compton effect's waves produced are very vital in X-rays that we use every day today in hospitals and local care facilities. The Compton effect can be used to calculate a wavelength of an X-ray with the given angle, or vice versa, calculating the angle of an X-ray with the given wavelength. Now, in order to do this, we need some sort of equation or numerical system in order to calculate wavelength and the angle. So, we have the following equation. We have the shift in wavelength equals the final wavelength minus the initial wavelength. And that equals the height of the wavelength over the mass of the electron times c times 1 minus cosine theta. me is the mass of the electron, and theta is the angle between the directions that the incident and the scattered photons travel. H over MEC is the Compton wavelength, and has a numerical value of 0.00243 nanometers, so it's almost negligible. Now that we have an equation for the Compton effect, we will now use the equation to solve an example problem where we find the wavelength of an X-ray given the fraction, and we find the fractional change of energy as well. Okay, so we have example problem 27.3. It says X-rays of wavelength of 0.2 nanometers are scattered from a block of material. The scattered X-rays are observed at an angle of 45 degrees to the incident beam. Part A says calculate the wavelength of the X-rays scattered at this angle. And Part B says compute the fractional change in the energy of the photon in the collision. Okay, so here we have example problem 27.3, and actually here we're going to start with part B, which is finding the total fraction of energy gained or lost. So right now we have energy equals HF, and that equals H times C over lambda, or wavelength. And so then we have delta E over E equals EF minus EI over EI, and that equals HC times lambda F minus HC times divided by lambda initial. Excuse me, the first one should be divided by lambda F. And that is all over HC divided by lambda initial. And then we have the change in energy over the energy equals 1 divided by lambda F minus 1 divided by lambda initial over 1 divided by lambda initial. And that equals lambda initial over lambda final, which equals minus 1, which equals lambda initial minus lambda final over lambda final. And that all together equals the change in the wavelength over the final wavelength. And then plugging in the numbers we have the change in energy over the energy equals negative 0.000711 over 0.200711. And that altogether equals negative 3.54 times 10 to the negative third, or negative 3.54 times 10 to the negative third loss in energy, loss in joules. And then now we move on to part A. And we have our fundamental equation for the Compton effect. The change in wavelength equals h over MEC times 1 minus cosine theta. And we plug in the numbers for that. We have change in wavelength equals 6.63 times 10 to the negative 34th, which is the standard number for h, over 9.11 times 10 to the negative 31st, which is the mass of a standard electron, times 3 times 10 to the 8th meters per second, which is the speed of light, or c, all times 1 minus the cosine of 45 degrees. And then after doing that, we have the change in wavelength equals 7.11 times 10 to the negative 13th meters, and that equals 0.000711 nanometers. Then we have the final wavelength equals the wavelength plus the change in wavelength plus the initial wavelength. And then plugging in the numbers, we have the final wavelength equals 0.2 nanometers, which was the given, plus 0.000711 nanometers, which was the variable we solved for, which equals 0.200711 nanometers as the wavelength, given that we have an angle of 45 degrees. And for those of you who are wondering where the negative 0.000711 came from in part B, that is the change in wavelength that we solved for in part A when we were solving for the wavelength, given that we had a cosine of 45 degrees.
Alright, so the main reason the Compton effect is important is because it explains that light cannot solely be classified under waveform. It also travels in packets of light called photons.
Okay, so here's a illustration that I found of the Compton effect. So it starts off with the incident photon, and the incident photon is labeled as lambda I, or the initial wavelength. And see at the bottom, it's kind of fading away right now. We have the initial equation for the Compton effect that I explained earlier. And so in the illustration, the incident photon is coming in contact with the target electron at rest. And since the target electron is at rest, as I explained with the basketballs earlier, the incident photon takes its momentum and energy into the electron at rest, and the collision between that makes them split off. And the angle on the bottom right, which was labeled theta, that is the angle between the directions that the incident and the scattered photons travel. So if we were doing an equation to find like the wavelength or whatever the unknown variable was, we would use angle theta, whatever the numerical value of that is, to solve for it and plug that into the equation, as opposed to the other Greek letter above that, which I'm not exactly sure what it is at the time.
Alright guys, so I think that just about wraps up my explanation of the Compton effect. I hope y'all gained something out of this, and I hope y'all at least have like a basic idea of what the Compton effect is, like why it occurs, how it happens, and its real world applications, especially with x-rays. Thank you for listening, and I hope you enjoyed it.